Okay, so this is lecture 20, and in this lecture we're going to talk about CSPs, which means constraint satisfaction problems, and we're going to talk about approximation algorithms for them. So when we were last talking, we were thinking about the max cut problem, which is going to turn out to be a particularly simple kind of constraint satisfaction problem, or CSP. And we spent a lot of time developing a semi-definite program for it, which is a generalization of a linear program. And we got as far as understanding that this would let us attempt to solve a max cut problem by finding vectors associated to each vertex that had some properties. And now we're going to talk about how we can try to take these vectors and convert them into an actual cut of good value. So let's recall what was going on. Let's phrase the max cut problem in the following way. So you're given a graph, an undirected graph, G, and you're supposed to partition the vertices into two parts, often called S and S complement. But in this case, we're going to call them all the vertices assigned value 1 and all the vertices assigned value -1. So we're going to assign values xv to the vertices plus or minus 1. And what we're trying to do is maximize the number of edges that have their endpoints on different sides of the cut. So in other words, we want to maximize the sum over all edges, VW, just of the indicator that we've assigned different cut sides to the two endpoints, V and W. Okay. Sorry, I'm getting some, can everybody make sure their mic is muted, please? Thanks. Okay, so, right, so last time we developed what was called a semi-definite programming relaxation for this problem. And what was that? Well, here it is up on the screen. We want to, we're going to have, in a semi-definite program, we're going to have variables, n-squared variables, one for each pair of vertices, and we call these little y's sub VW. And we think of them as being arranged into a matrix. And the idea is that YVW is supposed to stand for the product of XV and XW. Sorry, I'm still getting people who are unmuted. Okay, can everybody still hear me? I've tried to mute you all. Okay, so right, so YVW is supposed to stand for XV times XW, which is this quantity up here. And so we have a linear objective function involving the variables YVW. And since XV and XW are supposed to both be plus or minus 1, XV times XV should always be 1. So we can put this as a linear constraint, YVV equals 1. And also XV is the same as XW, so we can put the constraint that YVW equals YWV. Okay, I just wrote that down here, because the main constraint we had was that Y is a positive semi-definite matrix, which we talked about last time. And the point of this is it's a relaxation of this condition that we want. So it's a relaxation of the condition that there exist real numbers, one for each vertex, XW, such that YVW equals XV times XW. Okay, so as we argued last time, you can solve this semi-definite program and find the optimal YVWs here in polynomial time. Okay, maybe up to some like exponentially small additive accuracy, but we can ignore that. Great. So we also talked last time about what is a positive semi-definite matrix, and a square matrix is said to be positive semi-definite, assuming it's symmetric matrix, if and only if we have this condition. This is one of the equivalent conditions we talked about last time. If and only if there exists some vectors, little u1 through little un, such that the VWth entry of the matrix is equal to the dot product of the Vth vector with the Wth vector. Okay, so the existence of these vectors, whose dot products, all whose pairwise dot products give you the matrix Y, is equivalent to being PSD. And I've written here that these vectors, of which there are n, should themselves be in n dimensions. This statement is true. It's also true if I eliminated this condition that they be in n dimensions. So just if you have vectors in any dimensions, n vectors in any dimensions that have this relationship, their dot products give you the entries of Y, then Y is PSD. But on the other hand, if such vectors exist, as we argued last time, they can all exist in n dimensions. Now, what's interesting here in the you can look back at this claim that it's this SDP condition is that it's a relaxation of this goal that there should exist numbers xv such that yvw equals xv xw. If we could somehow insist that these vectors be one-dimensional vectors, i.e. numbers, then this PSD condition would be exactly equivalent to what we're shooting for. And if we had this exact condition about numbers xv, this would exactly be capturing the max cut problem. But alas, we cannot solve that program in polynomial time. But with this relaxation where we allow, these xv's, which we're now calling uv vectors, to be vectors in like a large dimension, it almost looks like a more complicated problem. But interestingly enough, we can actually solve this program in polynomial time. Any questions right now? As always, you can type them into the chat and I'll catch up with them when I need to. Okay. So let me just make a few changes of notation. Instead of writing y sub vw down here and insisting that the matrix of y's is positive semi-definite, I'll just use this equivalent constraint about positive semi-definiteness. So this maximization problem is now maximizing over vectors, one vector per vertex in the graph. So we're given the graph, and this program is now to find vectors, one vector for each vertex in the graph. And what are the constraints we have? Well, the only constraint really we had left was that the yvv was supposed to equal 1. So that's saying that the vth vector dotted with itself should be 1. And it's like saying the length of the vth vector squared is 1. And so that's just equivalent to saying that the vth vector is a unit vector. Okay, so I'm just changing this notation a bit more, but now we can see this SDP relaxation, which we can efficiently solve, is seeking a unit vector for each vertex in the graph, and it's trying to maximize this objective function. The sum over all edges, if you look at the vectors for the endpoints, use of v vector and use of w vector, and you dot them together and you take a half minus a half of that. Now let's think about this a little bit more as well. So these are unit vectors, so their dot products are going to be between -1 and 1. Well, actually, I'll come back to that in a second, but let me do this, as it says on the slide, this relaxation check. I want to check that this program is still a relaxation. So first of all, what it means to be a relaxation is that the optimum, the actual max cut in the graph, should have value less than or equal to the semi-definite program's optimum. And I claim that's true because suppose you have any cut, some subset of vertices S, which achieves the maximum cut, that achieves this optimum value. Now, what solution can we get for this SDP? Well, I'll just take all the vertices that are in S and assign them like the fundamentally one-dimensional vector that's like +1 in the first coordinate and 0s elsewhere. And all the vectors, sorry, all the vertices that are not in S, I'll assign them for a unit vector, just -1. Okay, so these are definitely unit vectors. They're all lying in a line. And so they're feasible solutions since they're unit vectors. And you see, if you have an edge, VW, where V and W are on the same side of the cut, then the vectors associated to them will be the same. And so the dot product will be 1. And so this expression, half minus half the dot product, will be 0. So you'll indeed sort of get like 0 points for this edge where the endpoints are the same. But if the endpoints are different, the dot product will, of course, be -1. This linear expression will be 1, and you'll get like 1 point, indeed, for this edge. Okay, and so this says you can always take a feasible like integer solution, like a cut, and turn it into one of these vector solutions that has the same value. But, this SDP opt could be bigger because, well, these vectors don't have to be one-dimensional. They can be n-dimensional. So maybe you can make things bigger. And in fact, you can, as we'll see. On the other hand, I mentioned, since all the feasible solutions use unit vectors, this dot product will always be between -1 and 1. In particular, it'll be at least -1. So this linear expression, half minus a half times the dot product, will be at most 1. Oops, this is a typo. It should say the optimum is at most m, the number of edges. Okay, that's because you get, I'll draw in white here, you get at most 1 for every edge. Okay. So let me make now a really kind of slightly gross but useful abusive notation. Before I was calling these vectors, one for each vertex. If the vertex was v, I was calling the vector u sub v vector. Now I'll do something like a little wacky, and for a vertex named v, I'll call its associated vector v with a vector sign. Kind of a weird abusive notation, but it's actually kind of nice. So now what I'm going to say is we want a unit vector for each vertex, and the amount that you get for it is just for the edge with endpoints v and w is just the dot product of the associated unit vectors. And let's think about this dot product a little bit more. If you remember high school algebra, the dot product between two vectors is the product of their lengths times the cosine of the angle they make. But these are unit vectors, so the product of their lengths is just 1. So the dot product is really nothing more than the cosine of the angle between them. As we've seen before, like, if v vector equals w vector, then you get +1. And if v vector is minus w vector, then you get -1. But for example, if v and w are orthogonal, which they can be once you go to higher dimensions, their angle is 90 degrees, the cosine of 90 degrees is 0. So like if you have two vectors that are orthogonal and they're forming an edge, you kind of get half a point for them. You get half minus a half times 0. So this geometrically, like these vectors, you have a vector for every vertex, and if like they're antipodal, you get like 1 point if there's an edge, and if they're the same, you get 0 points. If they're orthogonal, you get half a point, and everything in between. So this is what the plot of cosine theta looks like as theta goes from 0 to pi. Okay, so you're trying to embed this graph into like the unit sphere such that the edges are as far apart as possible. Their endpoints are as far apart as possible. So let's do an example, a pretty simple example, but kind of an interesting example. So this example is a 5-vertex graph. It's just the 5-cycle graph, and I've called its vertices A, B, C, D, and E. And so in this problem, you're looking to assign a unit vector to like 5 vertices, such that the ones connected by edges are sort of as far apart as possible. Turns out the optimal solution for these vectors occurs in 3 dimensions. And it's actually got a name. It's called Lovász's umbrella, because László Lovász came up with this for, well, a related sort of problem in coding theory. So yeah, so it's, he called it an umbrella. You see, so this peak of the umbrella is the origin in 3 dimensions, and then like the 5, what are they called? Some things of the umbrella? Spokes? Not spokes, there's a word for them. Anyway, these 5 spokes of the umbrella are the 5 unit vectors. Okay, so I guess they're all pointing, sort of down. And I haven't actually said which vector is associated to which vertex. And you see, actually, it's not the first thing you might think of. It's not like you just put the vertices like A, B, C, D, E around the spokes of the umbrella. Ribs, I think they're called ribs, the ribs of the umbrella, because you want, if it's an edge in the graph, you want these unit vectors to have as big an angle as possible. So in fact, let's say you call this vector here A. Let me get the highlighter out. Oops, not the highlighter, the laser pointer. Let's say you call this first vector A. You may as well do that without loss of generality. So then now let's decide where to put B. So you actually, since AB is an edge, you want to put B as far apart from A as you can. Now, bearing in mind that I've already told you the optimal solution happens to look like this, it means that B should be one of these 2 edges here, sorry, vectors here. So let's say this is B. And then B and C have an edge, so you want C to be sort of as far from B as possible. And you don't mind if C is close to A because they don't have an edge. So perhaps this is C, and then you want D to also be far, and you want E to also be far. And this is it. This is actually the optimal solution. I mean, it's not obvious or anything, but it turns out to be true. And you see that in this solution, every edge in the graph is associated to 2 unit vectors whose angle is, well, as far apart as possible in this umbrella. And if you do a little geometry, it turns out to be 4 pi over 5, aka 144 degrees. So this is the optimal solution to the semi-definite program for this 5-cycle graph. And cosine of, I mean, now we take a look at what it achieves. It turns out that cosine of 4 pi over 5 is negative phi over 2, where phi is the golden ratio, 1 plus root 5 over 2. And numerically, this is about negative 0.8. So it's pretty good, right? So like every edge in the graph, all 5 edges in the graph are associated to unit vectors whose dot product is around negative 0.8, which is good. I mean, the smallest it could be, which is what you're shooting for in terms of dot products, is negative 1, and you got negative 0.8. So a half minus a half times negative 0.8 is positive 0.9. So like this sort of vector solution, it kind of like 90% cut each edge in a weird way. And therefore, oops, this was me messing around. I don't know why that's on the slide. Ignore this. Right, so what's the integer solution? The actual solution here, the optimal cut, is 4 edges, because this is not a bipartite graph, so it's impossible to find a partition that cuts all the edges, but you can get 4 out of 5. Is there a question? Okay. But the STP opt is this like approximately 0.9 times 5, because every edge is achieving this 0.9, so the STP opt is around 4.5. Okay, so this is an example where the STP really is a relaxation in the sense that the STP gets a value that's bigger than the optimum, but it's still kind of non-trivial. And just out of interest's sake, the ratio here, 4 over 4.5, is around, well, it's like 8/9, it's around 0.88, or more accurately, it's exactly this number. Right. Okay, so this is an example of a solution to the semi-definite program for max cut on this graph. And now let's talk about this concept of rounding. So again, when we were solving problems before with linear programs, we'd take an integer program, relax it to a linear program, get some kind of like fractional solution. And then what we tried to do was like convert or round this fractional solution to an integer solution, like a real solution, where the value of that solution was as close to the LP value as possible. Okay, and we're going to try to do that again here, except instead of like a fractional solution, we have a vector solution. But we're again going to try to round these vectors down from n-dimensional vectors to like one-dimensional numbers, plus or minus 1, and this will give us a cut. Okay, so there's a very beautiful, natural, and elegant way to do this, given by Goemans and Williamson in this famous paper from 1994. And it's this. You have all these vectors in space that you've gotten out of solving your STP, and you want to partition them into 2 parts. So what you can do is pick a hyperplane through the origin. And since, we don't really know much else to do, or like maybe the easiest thing to do is just pick a random hyperplane through the origin, one that's like rotationally symmetric. So just a random hyperplane through the origin. And yeah, that splits your vectors into 2 parts, and therefore it splits your vertices into 2 parts, and just let's call those our parts, S and S bar. So this is a cut. And now we have to analyze this, or we would like to analyze this and understand, in expectation at least, what number of edges can we expect this to cut. And just as a little callback to, I don't know, lecture 3 or something, algorithmically, how do you actually pick a random hyperplane through the origin? Well, a hyperplane, you can associate a hyperplane with its normal vector. And you can get a random normal vector just by picking all the n components to be Gaussian. So remember, this most important fact about Gaussians is if you pick n of them independently, the resulting vector is like rotationally symmetric. So algorithmically, the way you actually execute this line of the code is to just pick n Gaussians and consider the hyperplane orthogonal to them. In particular, actually, you put every vertex into S if its vector, v vector, makes a positive inner product with g vector, and a negative if you put it into S bar if it makes a negative dot product with g vector. Okay, so let's talk about the analysis. And what do we really want to do with this analysis? So we haven't given some vectors. There's two things going on. First of all, these vectors achieve some value for the objective value for the semi-definite program. Namely, they achieve the sum over all edges of this expression, half minus a half times the cosine of the angle between the endpoints. And we have this algorithm now that produces a cut, and we are interested in like how many edges it cuts. And we want to bound that in terms of this SDP expression, objective expression. So this is what we care about, the expected number of edges cut by this random hyperplane rounding algorithm. Okay, so we can write this as the expectation over the random hyperplane of the sum over all edges VW, just of the 0, 1 indicator random variable that S cuts the edge VW. That one of V is in S, one of V and W is in S, and the other is not in S. Okay, so as always in life, whenever we see this expression, you should switch the expectation and the summation, and then you'll have expectation of an indicator, and the expectation of an indicator is a probability, so you'll get to this expression. So it's the sum over all edges of the probability, again, over the choice of the random hyperplane through the origin, that, well, S cuts this edge, according to the algorithm, if and only if the two vectors, V vector and W vector, associated to these vertices by the SDP are on opposite sides of the hyperplane. Okay, and what's nice is we can now analyze this on an edge-by-edge basis. So we can like fix an edge, VW, in our minds, and the associated unit vectors, V vector and W vector, and ask, like, what's the probability that a random hyperplane will split these two vectors? So here's a two-dimensional picture. Of course, it's really in n dimensions. But actually, in another sense, it's really in 2 dimensions, as you'll see. So here's the unit sphere, and we have 2 vectors, V vector and W vector. And we're picking a random hyperplane through the origin. And in fact, really, it really is 2-dimensional in the sense that, like, if you think about this geometrically for a minute, whether or not a hyperplane, splits these 2 vectors, I don't know if my hand gestures are going to make a difference. It really only depends on where the normal vector to the hyperplane is when projected onto the 2-dimensional plane spanned by V and W. Didn't say that super well, but the upshot is, picking a random hyperplane, once you fix V and W in your mind, picking a random hyperplane, you can really do it analogously just by picking a random, hyperplane or line in the 2-dimensional plane where V and W live. And like this, orange line that I've just spun here. And once you have this geometric realization, it turns out there's a very simple expression for this probability. You see, there's basically like 180 degrees of possibility for how this orange thing rotates. And the event that they get split, occupies an angle of the angle between V and W. So what I'm saying here is this probability, once you fix V and W, the probability that they're split by a random hyperplane through the origin is precisely their angle divided by pi, or 180 degrees. Once you get down to this 2-dimensional case, I think that should make sense, right? Like if V and W were at angle 0, then the probability that this hyperplane would split them is 0. And if V and W were at angle 90 degrees, see if I can draw it here. If V and W were at angle 90 degrees, like V was this, okay, then, the probability that the orange line would split it would be like sort of, only if the orange thing was going like this, it's a 50% chance. And again, if V is like this, if V is actually opposite to W, then there's a 100% chance that they'll get split by a random diameter of the circle like this. Does that make sense? Any questions? Good. So this is kind of cool because we have like an edge-by-edge expression for both things. An edge-by-edge expression for the SDP objective value, that's this, and an edge-by-edge expression for like the expected contribution to the total cut value. the probability that the edge gets cut by the algorithm. And so, and they're both in terms of just the angle between, I mean, this is also key, just involve the angle between the two vectors. So now it's just like some numeric comparison between this magenta thing and this green thing. So let me put this back up here. Expected number of edges cut by the algorithm is the sum of this purple or magenta expression. And you can just plot these two quantities as a function of the angle theta. So, any two unit vectors, their angle is somewhere between 0 and pi, 0 and 180 degrees. And the probability that these vectors get cut by the algorithm is like a linear function of their angle. If they're at angle 0, it's 0. If they're at angle pi, it's 1. So it's just this expression up here, theta over pi. But the SDP, the contribution of the semi-definite programs value is this nonlinear thing. It's half minus a half cosine, so it looks like this curve. The point is that these two expressions are not the same, but they're pretty close. They're not too different. In particular, if you look at the ratio between these two expressions, you're worried this SDP opt could be bigger than the actual thing you found, but it can never be like that much bigger. This green line is never that much higher than the magenta line. And in particular, the worst ratio between them occurs at this point that's really, really close to 3/4 pi. It's a teeny bit less. It's here. And even here, the magenta point is like 0.878 times the green point. Another way to say it is if you multiply this green curve by 0.878, which I've done in a charmingly homemade fashion here, freehand, you get this slightly darker, slightly thinner green curve, 0.878 times the expression with the cosine. And this new curve fits underneath the magenta line. Which means that the magenta expression is always greater than or equal to 0.878 times the green expression. Okay, what I'm using here is the fact that this magenta line is above this lower green thing, 0.878 times the green expression. Okay, and so now you can bring the 0.878 outside the sum, and you'll get just exactly the SDP objective function. So you conclude that the expected number of edges cut by this algorithm is at least 87 or 88% of whatever the SDP optimum is. And the SDP optimum is always bigger than or equal to the true optimum. That's because the SDP is a relaxation of the max cut problem. So this in turn is bigger than 0.878 times the optimal max cut. Okay, and this is like the end of the analysis of the Goemans Williamson SDP rounding algorithm. And it says, or one way to succinctly say what's going on here is this Goemans Williamson algorithm, this GW algorithm, is a so-called 0.878 ratio approximation algorithm for max cut. So at least in expectation, it will give you a cut whose value is at least 87.8% times the maximum cut. Okay, and you can run this many times and take the best cut, and you'll get this to hold not just an expectation with high probability. You can even de-randomize this using Nissan's small set generator, a small space generator, and some other ideas if you like. Okay, any questions about that? Okay, there's a question. It says, is there any particular reason why we consider r to the n instead of some other dimension in the relaxation? Say r to the log n. It's still a relaxation. Great question. So remember, yeah, in the relaxation, the SDP relaxation, it eventually turns out to be, find a unit vector for each vertex to maximize this expression. And so to answer the question, it's sort of not up to us what dimension the solution ends up being in. If we could specify, not only do I want this, but I want these vectors to be in dimension D, then we'd actually be solving an NP hard problem, because we could say, oh, I want them to be in dimension 1, i.e. that I want them to just actually be scalars. And in that case, as we saw, the vectors, since you have that their dot products is 1, they have to be unit vectors. They would have to just be the numbers plus or minus 1. And then you would exactly get that the SDP captures the max cut problem, which is NP hard. So in some sense, it's like not really up to us. We have to allow them to be sort of any dimension. it's weird because by like saying like, I give up, they can be in any dimension, it actually makes it polynomial time feasible to like find the optimal vector solution. And as a side note, it's not like they're going to be in like exponentially many dimensions if you, think about the nature of positive semi-definite matrices for a moment, as we did last time. If some dot products can be realized, if you have n vectors realizing some pairwise dot products in any dimension, then they can be realized in n dimensions. As we saw last time, if you do this Cholesky decomposition on the Y matrix you get out of the semi-definite program, you get back n-dimensional vectors. Good. On the other hand, related to the question about whether they could be in lower dimensions, it's also true that if you solve the semi-definite program and unfortunately get vectors in n dimensions, you can it's like a known fact, this Johnson-Lindenstrauss lemma, if you've ever heard of it, that you can randomly project these vectors down to around log n dimensions. And the dot products will, with high probability, not change by very much. So actually, you can get them down to like log n dimensions. But in some sense, it doesn't help that much. OK, great. So now I want to go on, and as the title of the lecture suggested, talk about constraint satisfaction problems more generally. In some sense, maxcut, which we've been focused on for a while, is almost like the simplest constraint satisfaction problem. So now I want to talk about them more generally and about approximation algorithms for them more generally. And I'll start calling them CSPs. That stands for constraint satisfaction problems. OK, so constraint satisfaction problems are a pretty wide class of algorithmic problems or tasks. And many well-known algorithms problems are examples of constraint satisfaction problems. So the maxcut problem is a constraint satisfaction problem, and the 2-sat problem, and the 3-sat problem, and the k-sat problem are CSPs. Trying to 3-color a graph is a CSP. Trying to solve a system of linear equations is a CSP. Not every problem is a CSP, but a lot of cool problems are CSPs. So in order to say, instead of just directly diving into the definition of CSP, which is a little bit elaborate, let me talk about 2-sat specifically for a moment and why it's a CSP. It'll help us learn some of the terminology. So remember the 2-sat problem. I'm sure you've heard of it before. The input looks like this. It's like a 2CNF formula of a bunch of variables, x1 through xn, and a bunch of clauses, each of which is like the OR of 2 literals. And you're trying to find a truth assignment that, ideally satisfies all of these clauses. So what are some of the ingredients of this 2-sat problem, or the input? Well, first of all, the one ingredient is the variables, x1 through xn. Another ingredient is what I like to call the domain. The domain is like the values that you're trying to associate to the variables. Okay, so sometimes in, the SAT problem, you call them 0 and 1. Sometimes you call them true and false. Let's just call them true and false for now. So in 2-sat, you're trying to assign true or false to every variable. And well, the other main ingredient in 2-sat is the clauses, which we're going to call constraints because we're going to start talking about CSPs. And each one is a constraint. It's because they're ANDed together. This clause is a constraint, like you want x1 and x3 to have a true OR, and you want this clause thought of as a constraint to be true of your assignment, and you want this clause to be true of your assignment. I should say, by the way, it's going to come up again, but there's an unfortunate behavior in algebra and constraint satisfaction problems in that people don't make a clear distinction between a variable and an assignment to a variable. But we're going to try to keep those two things very separate in our heads in today's lecture, the difference between a variable and an assignment to a variable. OK, so in 2-sat, it would seem that you just say, OK, yeah, you can have any number of clauses or constraints, and each one should be the OR of 2 literals. But in order to define constraint satisfaction problems in general, I really don't want to talk about literals. If you recall, a literal is a variable or its negation, but I don't want to talk about negations. I just want to talk about variables. So in fact, I don't want to say that the constraints are ors of two literals. I want to say it differently. So let me call, in my little example here, let me call the clauses or constraints, as I'll start to call them, C1, C2, C3, and so forth. So let's take a look at C1. C1 is nothing too funny. C1 is the or function, or the or predicate, or the or constraint, or the or relation. Those are all synonyms, applied to variables x1 and x3. Okay, what about C2? I want to claim that C2 is also some predicate or relation, or little function, applied to variables x2 and x4, but I don't want to mention literals. So does anybody know what predicate is being applied or is constraining x2 and x4 here? You can type it into the chat. All right, well, for those of you who just want to enjoy the show, it's NAND, right? This constraint is specifying that they can't both be true. X2 and X4 cannot both be true because that's when this clause fails, this or fails. Yeah, very good. Somebody got it, NAND. There's just a little lag, I suppose, between when I ask and when people quickly type. Great, so what about C3? C3 is another clause that's somehow constraining X2 and X11. What variable or what predicate is constraining X2 and X11 here? Check in the chat. I guess it's like some implication or something, like maybe implies or something, but I want to start talking about it this way. Let me just call it this. It's like the or function, except you negate the first input. Okay, that's what's going on here. In other words, it's the the predicate with this truth table. Yeah, I suppose that's commonly called like implies, but yeah, very good. Somebody said it on the chat. But yeah, I think what's best is to think about it is like actually in 2SAT, there's like 4 kinds of constraints you might have. Each one is sort of like the or constraint on 2 variables, except that you're allowed to have negations on inputs. Okay, so instead of making a literal into a first-class object, I just want the variables to be first-class object and talk about changing the constraints. So in the 2SAT problem, you don't have like one kind of constraint, like or of 2 variables or literals. I want to say that you have a set of 4 allowed constraints, or but with the second input negated, or but with the first input negated, and or but with both inputs negated. And each of these 4 constraints has what I'll call arity to. Arity means just the number of variables to which the constraint applies. And actually, to be super technically correct here, the CSP I'm describing is usually not called 2SAT. It's usually called E2SAT. This E referring to the fact that every constraint involves exactly 2 literals. It's a very minor point. Well, it's not so minor, but it's a technical point. Usually when people just say 2SAT, they allow clauses of length up to 2. But for now, we're describing, the version where every clause has to have exactly 2 constraints. So instead of writing the input like this, is like, first of all, I'm not going to write it as a conjunction. I'm just going to write it as a list of constraints that I want to be true. And yeah, each of these constraints, I'm going to say, okay, it's one of the predicates or constraint types from my set applied to, in this case, 2 of the variables. Okay, and these pairs of variables are called the scopes. Like in this first constraint, the or with no negations is the predicate, and the pair x1, x3 is the scope of this predicate. And again, just as this minor point, in the formal definition of CSPs, the scopes are required to involve distinct variables, which is why this really only lets you have it's like E2SAT, you're only allowed to have ors of 2 distinct literals. You can't do this trick of like, oh, if you want to just have the constraint x1, I'll just do or of x1 and x1 because I want the scopes to be distinct variables. Okay, so in light of that, if you want to capture just plain 2-sat, where you're allowed to also have clauses of length 1 and literals of length 1, then you have to add 2 more predicates of arity 1, which you could call or and sub 1 and or sub 1 with negation. Or like, I guess it's like the identity function on one variable and the negation function on one variable. Okay. So let me give the formal definition now, and this is like it's like a sort of annoyingly complicated definition. So if you have any questions, definitely type them into the chat. So in general, a CSP is defined by a couple of things. First of all, the domain, which I'm going to call omega, and remember this is like the values you want to assign to the variables. So this domain was true and false for 2-sat or sat-like things, but like for 3 coloring, the domain is going to be like red, green, blue. And it's most often just like the integers from 0 up to some q minus 1, and often q is 2. So it's like often you're concerned about like binary constraint satisfaction. Sorry, I should say Boolean constraint satisfaction problems where you're trying to assign like 0 and 1 to every variable. But the main thing that defines a CSP is the set of predicates that are allowed, sort of the set of constraint types that are allowed. And I'll call this capital psi. And this set can have 1 or more predicates in it. Like for E2-sat, it had 4 predicates. And every little psi in this set is a mapping from like an R tuple of domain elements to 0 and 1. And here 0 and 1 means satisfied and unsatisfied. Okay, and R is the arity of the constraint. So remember, like for the 2-sat or E2-sat CSP, omega was true and false. All the arities were 2. So our constraints, little psi, we're supposed to map a pair of true-false values to 0 and 1, meaning satisfied or not satisfied. And indeed, like, you know, the first one of the 4 constraints was the or function, which maps a pair of truth values to 1, unless both those truth values are false. And you can have different arity, your size and your big predicate set can have different arities if you want. Like if we wanted to capture 2-sat, remember we needed some or type predicates of arity 2 and 2 or type predicates of arity 1. That's fine. And that's it. So once you define the domain, and most especially the set of predicates, that defines a particular kind of CSP, like, as we'll see, max cut or 3 coloring. So that's like the problem, but now you have like an input or an instance of the problem. The input or an instance of constraint satisfaction problem is, well, it's like a set of n variables, which we'll just call v, together with a list of constraints. And the list of constraints is the main thing. And think of like the clauses in our 2-sat instances. Each constraint C is a pair. I usually write the other way, psi s. I'm not sure why I wrote s psi here. Anyway, psi is one of the predicates from the set. It'll have some arity R, and s is the scope. And the scope, remember, is a tuple of distinct variables, and there should be R of them for a predicate of arity R. Okay. Good. So that's all the terminology involved in a CSP. And my computer is really chugging. It freezes at the start of each new slide. Okay. So let's see some examples. So one, I said, one of the simplest possible examples is max cut, and that's true. So max cut, well, on one hand, sometimes we describe it, oh, you're given a graph and you want to partition the vertices into 2 parts to cut as many edges as possible. But you can really think of that as a CSP as well, where the vertices of the graph correspond to variables, and the edge of the graph corresponds to constraints. So it's like a funny way to write a CSP. So there, the domain, I should say plus or minus 1. It's a little bit of a funny typo. The domain is plus or minus 1. If you imagine you want to assign, let's say, +1 and -1 to each vertex. And the predicate set only has 1 predicate, and that predicate is the not equals predicate. which maps a pair of plus or minus 1 values to, satisfied or unsatisfied. Okay, it's really like capturing max cut, right? You want to assign 2 values to each of the vertices, and you want to, every edge is saying like, please cut me. It's like saying, please assign my vertices not equals satisfying values. Okay. What about 3-sat? So 3-sat is one of my favorite CSPs, it's classic. And you can call this domain true false if you want, but let me switch now to maybe the more standard computer sciencey way of describing it, where the domain is 0, 1. So you're trying to assign 0, 1 values to all the variables. And remember, now to accurately capture 3-sat, you need like a lot of constraint types. You need all, because you're not allowing literals, so you have to build it into the constraints. So you're allowing you can OR together 3 variables, or you can OR together 3 variables, but like put a negation on the third one. And there's like 8 ways to do this, ending with you can OR together 3 variables while negating all the variables. And then there's all because in 3-sat you usually allowed clauses of size 2 and 1, so there's all the 4 OR type functions of arity 2, and there's all the 2 type OR functions of arity 1. Okay, so 3-sat, when you write it as a CSP in this way, like the predicate set, capital Psi, has 14 predicates in it. On the other hand, if you care about E3-sat, that again just refers to all the clauses having to have length at exactly 3, and so then Psi would just have the 8 arity 3 kind of ORs. That's a pretty cool constraint satisfaction problem is called NAE3-sat. And there again, it's kind of like 3-sat. The domain is 0 and 1. And Psi is also going to have like 8 constraints, but I'll just say it's like you take the NAE3 predicate, plus you allow literals. And what is NAE? It stands for not all equal. So the not all equals predicate is satisfied if, well, the truth values x, y, and z are not all equal. So it's unsatisfied if they're all equal and 1 otherwise. Okay, so it's kind of like a weakening of 3-sat. Like in 3-sat, an OR is satisfied if you get at least one of the literals to be true. And not all equals 3-sat, you want at least one literal to be true and at least one literal to be false. Maybe I guess it's a strengthening of 3-sat. Anyway. 3 coloring is a very popular algorithms problem. It's also a CSP. So here the domain, again, it's like you think of it on one hand as like a graph. You're trying to color the vertices with 3 colors. But again, you can think of the vertices as variables. And the domain is like red, green, blue. So you're trying to assign one of 3 colors to each vertex. And each edge is just insisting that its endpoints get not equals colors again. So here again, the predicate set only has 1 predicate. It's the not equals predicate. Although formally, this is not equals predicate that takes a pair of colors and outputs whether or not they're unequal. Let me tell you one more CSP. There are plenty of others. I'll tell you one more. It's not quite a standard name, but I'll call it bijection parentheses Q. So in this CSP, the domain is just a set of size Q. You can call it 0 through Q minus 1. And what predicates are allowed? You actually allow a lot of predicates. They're all binary predicates. So they take 2 values, let's call them A and B. And any Psi is allowed so long as it has what's called the bijective property. And that means it should be that for every little a that you plug in for the first value for Psi, there should be a unique B that makes Psi satisfied. Okay, so for example, max cut has this property because with the not equals constraint, over a plus or minus 1 domain, like no matter what you assign for like a first vertex, there's exactly 1 way to assign the other vertex to satisfy the constraint. Okay, but it doesn't have this property in 3 coloring, right? Because if you assign one vertex red, there isn't a unique, correct way to assign the other one. You can do green or blue. But max cut is an example with this property, or if you have like a constraint that's like an equation, xi minus xj equals 7 mod q. This is also a bijection constraint. Xi minus xj equals 7 mod q, because for every assignment to xi, there'll be a unique value assignment for xj that will differ from it by 7 mod q. And this CSP's real name, or most usual name, is this weird name, unique games. Okay, and it's related to this unique games conjecture you might have heard about, and which I'll talk about at the end of this lecture, briefly. Okay, so this is a bunch of CSPs. And okay, what are you trying to do with the CSP? Right. So given an instance I, this is my weird capital cursive I, you're trying to come up with an assignment. What is an assignment? It's a map F that assigns to each variable a domain value. Okay, and we say that a constraint C, psi comma S, is satisfied if, when you assign the variables in its scope according to F, the constraint outputs 1. Okay, so f of S is my shorthand just for F applied to each of the variables in the scope S. Further definition, we say the value of F is, I'm going to call it not the number of satisfied constraints, but I prefer to call it the fraction of satisfied constraints. Pretty much the same difference. So this will always be, I do that because I want the value of an assignment to always be between 0 and 1. And so like a funny way to write it would be you average over all the constraints of just the predicate applied to the scope with this assignment F. And that works because I have my predicates outputting 0 or 1 for whether or not they're satisfied. Okay, so then if you just average all these 0, 1 values, you indeed get the fraction of satisfied constraints. And finally, I'll say the optimum of the CSP, denoted opt of I, is, well, it's a natural thing. It's the maximum possible value you can achieve over all assignments F. Okay, so you're trying to find the assignment which maximizes the fraction of constraints that it satisfies. Okay, so like in maxcut, right, you're trying to find a partition that maximizes the number of constraint or edges that you cut. And you can even think of things like 3SAT as like a sort of optimization problem where you're given a 3 CNF instance. One thing you might think about is just whether or not there's an assignment that satisfies all the clauses. But more generally, you could try to find an assignment that satisfies as many clauses as possible. Okay, and we say that an instance is satisfiable if its optimum is 1, meaning there's an assignment satisfying 100% of the clauses or constraints. Okay, so I'm going to talk about 3 algorithmic tasks associated with CSPs. So one task given a CSP is the satisfiability task. And that's a simple task. You're given the instance, and you just want to decide if it's satisfiable, if the optimum value is 1. This is like the classic task associated with like the 3SAT problem. You're given an instance, is there an assignment that satisfies 100% of the clauses / constraints? And, you might also ask, if you find out that it's satisfiable, you might want to find a satisfying assignment. But actually, if you can efficiently decide if a CSP is satisfiable, then you can also efficiently find satisfying assignments for it. And that's by a self-reduction trick. You just try setting the first variable to some domain value and ask yourself again, hey, is it satisfiable? If so, great, freeze that assignment. If not, try the next assignment. And you can go through all the variables like iteratively and find an assignment that preserves the fact that the CSP is satisfiable. And if you're, don't mind about polynomial time, then this reduces the problem of finding a satisfying assignment to just deciding whether or not an instance is satisfiable. Okay, the second task associated with a CSP that I want to talk about is optimization. And nothing in this life is perfect, so maybe you run a satisfiability algorithm, or you try to, and you find it's not satisfiable. We still might want to try to find the assignment F whose value is as large as possible. Ideally, whose value is equal to the optimum value. That's optimization. And now this third one is maybe the kind of task you thought about least, but it's equally important. I call it certification. And it's this task. Given an instance I, output a number beta, which is as small as possible, but you have to be guaranteeing that you're outputting an upper bound on the optimum. So like an algorithm here is going to output like a number like 0.9 together with like an ironclad guarantee that like I analyze this instance and I'm confident the optimum is at most 0.9, 90% of the constraints. Even more ideally, it would be for you to output like some kind of like vivid certificate that the optimum is at most beta. But as long as you like output a number that's like 100% guaranteed to be correct, then we call you a certification algorithm. Okay, and of course your goal is to output a beta that's as small as possible, ideally one that's equal to the optimum value. Okay, so let's talk about each of these three tasks in turn, because there's interesting things to say about each of them. So let's start out with CSP satisfiability. So perhaps the most interesting question to ask here is, what's going on with the satisfiability task? Because sometimes, for some CSPs, you can do it in polynomial time, and for some CSPs, it's NP complete. And like, what's the deal? So for example, the satisfiability problem for max cut, I claim, is in P. Why is that? Well, in the satisfiability version, you're not sort of trying to find the optimal cut. You're just trying to ask, is there a partition that cuts 100% of the edges? And that's exactly equal to deciding, or equivalent to deciding, if the graph is bipartite. It means there's a partition of the vertices into two parts, such that all the edges go between the two parts. And as you imagine, there's a simple polynomial time algorithm for that. And I'll even say what it is in just a moment. On the other hand, like 3-SAT, it's the most famous NP complete problem. I give you a 3 CNF, I ask if it's satisfiable or not, that's NP complete. Okay, this not all equals 3-SAT problem is also NP complete. The 3 coloring problem is NP complete. So sometimes CSP satisfiability is NP complete, but sometimes it's in P. So in fact, this like bijection problem I mentioned is in P. And well, deciding if an instance is satisfiable is in P. And the reason is basically some kind of propagation algorithm. This actually includes an algorithm for max cut, because max cut is a special case of this bijection problem. Why? Well, you can just take any vertex in a bijection instance and try all the possible assignments for it. And for each one, like assuming this variable participates in some constraints, the bijection property of the constraints means as soon as you decide on a domain value for one variable, all the constraints, by the way, are binary. It forces a unique choice for all of the assignments, the variables that it participates with in constraints. So it like forces some other values if you're going to be fully satisfiable. And those in turn force some other variable assignments if in turn you're going to be satisfiable. And you can just propagate this and check if you ever get like an inconsistency. It's like breadth first search. And as long as you do that for like each connected component of the constraint graph, and as long as you like try every possible assignment for one of the vertices or one of the variables in each component, then you can decide efficiently whether or not such an instance is satisfiable in polynomial time. Okay, so yeah, so how can we tell the difference? So for example, 2-SAT, NP or NP complete? Well, this is definitely non-trivial, but you probably know that it's in P, actually. You can decide if a 2CNF instance is satisfiable or not. 3-lin mod 2. This is a CSP where you have like linear equations. Each linear equation involves 3 variables, and it looks like this, but everything is happening mod 2. This is a CSP. All the constraints have arity 3. The domain size is 2. This CSP is in P, because it amounts to solving a system of linear equations over a field to determine if it's completely satisfiable or not. What about 1 out of 3-SAT, where in each clause, instead of trying to get at least one literal true, you're trying to get exactly one literal true? NP or NP complete? Turns out it's NP complete. What about this CSP called order 10? This is the problem where every variable can be assigned a value between 1 and 10. There's only one constraint type. It's the less than constraint. So you have a bunch of, you can think of it like as vertices, and you have a bunch of edges, directed edges. And the directed edge implies that like, this head of the directed edge should be less than the tail of the directed edge. And you have to assign a value 1 through 10 to each vertex. Can you check if this is satisfiable or not? This is also in P. You have to think about why, but you eventually take this instance and do a topological sort of the graph and see if it has depth at most 10. Okay, so you can see that like there's lots of different kinds of CSPs, and sometimes their satisfiability problem is in P, and sometimes it's NP complete, and like, what's the deal? So let me tell you a little story about this situation. So in 1993, Feder and Vardy were thinking about this, and they made a conjecture, and they made the following conjecture. They conjectured that every CSP satisfiability problem is either in P or NP complete. And it sounds funny because I didn't really mention like a third possibility before, but there are third possibilities. You may know this theorem in complexity theory called Ladner's theorem, which says that assuming P does not equal NP, there exist NP intermediate problems, problems which are neither in P nor are they NP complete. But the Federer-Vardy conjecture says this does not happen for CSPs. Every CSP they conjecture is either in P or NP complete. So there's like the easy ones or the hard ones. And this became known as the dichotomy conjecture. And much later, 12 years later, Bulatov, Jevons, and Krokin, who had thought about it, well, many people had thought about it for some time, they proposed a strengthening of it called the algebraic dichotomy conjecture, which basically told you which CSPs should be in P and which ones should be NP complete. Like they gave you a rule. And this rule was very sophisticated. It was an algebraic rule using ideas from an area called universal algebra. But they basically gave you some like, abstruse algebraic condition such that if it was satisfied, they conjectured that this CSP satisfiability problem is in P. And if it's not satisfied, they conjecture that it's NP complete. And actually, strangely, this part of the conjecture was the easy part that was like known for sure. If your CSP doesn't have this problem, it was provably NP complete. What was missing was the hard part, is that these CSPs that do have this property are in P. So it's kind of a strange situation where people were conjecturing certain problems, those that satisfied this condition, had a polynomial time algorithm, even though they didn't know one. It's almost always just the opposite in complexity theory and algorithms, right? If you have like some problem and you can't figure out a polynomial time algorithm for it, you're like, well, probably it's NP complete. But here, they're like, we believe these CSP satisfiability problems are in P, although we don't know how to prove it. So there's lots of work on this conjecture. And let's see, it was proven when the domain size is 2, back in 1978, actually before it was even conjectured, by Schaefer. I think there's 2 F's in Schaefer. This is maybe a typo. So he proved that every Boolean CSP is in P or NP complete. And then in 2006, it was proven for CSPs where the domain is of size 3. And then in 2017, Bulatov and independently Zhuk proved it. So fantastic. So the dichotomy conjecture, in fact, the algebraic dichotomy conjecture is a theorem. It's true. Every CSP is in P or it's NP complete. And this weird algebraic condition tells you, given a CSP, which one it is. Interestingly enough, the meta problem, given a predicate set psi, does it satisfy this algebra condition or not that makes you in P? That meta problem is NP hard, I believe. But, well, anyway. Good, so that's all I want to say about CSP satisfiability, but it's an extremely interesting area. Okay, let me move on now to talking about CSP optimization, which is like the second task. So in contrast to CSP satisfiability, if I ask you to find, the optimum assignment, the one that satisfies the most constraints, even if that's not 100% of the constraints, this is really hard. It's NP hard for all but the most simple CSPs. I mean, it's already NP hard for max cut, as you well know. So in light of that, when things are NP hard, you have to try some mitigation strategies. And one of them is what's called approximation. So that's the mitigation strategy I'll talk about in this lecture. So let me make a definition. Let's say an efficient algorithm A for a particular CSP is an alpha beta approximation algorithm if it has the following property. For all instances where the optimum is at least beta, the algorithm A is guaranteed to find an assignment whose value is at least alpha. Okay? That's alpha beta. And I have this little mnemonic. I think of beta as standing for best. Like that's the best assignment achieves beta. And like for me, alpha stands for algorithm. It's like what the algorithm is promised to achieve in this case. Actually, let me put a little pause here because there's a question I was asked. Even if it is NP hard, presuming, even if it's NP hard, presumably meaning this meta problem of deciding whether a predicate leads to a P problem or an NP complete problem. Is it in exponential time? It seems like the description of a CSP is usually very short for the problem we care about. Right. Yeah, so it is in exponential time. It's probably in P space. And some version of it, if like, there's some simple property of the CSP. There's like a simple and natural property of CSPs called being a core, some algebra thing which I forget, which if it happens, then the meta problem is in P. But yeah, it is true that like for the CSPs like we actually care about, you know, they have, their description is like finite size, you know, there's like 14 predicates and the domain is of size 3. So like you don't have to really worry about, you can in practice decide if it's a P type or an NP complete type CSP. Yeah, so this meta problem is sort of of theoretical interest only. Okay, let's get back to CSP optimization. So this is my kind of slightly complicated definition of what is an approximation algorithm. And I built efficiency, like polynomial time, into the definition just so I can stop saying, oh, an efficient approximation algorithm, efficient approximation algorithm. I'll just assume when I say an approximation algorithm, it means a polynomial time one. And also I'm going to allow randomized algorithms, in which case the guarantee should be that it finds a value, an assignment of value at least alpha in expectation. And one thing I want to mention is that one algorithm A can simultaneously be an alpha beta approximation algorithm for many betas. And let me give a clarifying example. What do we prove? The first part of this lecture, we proved that this Goemans Williamson algorithm for max cut, what we proved is that it's a 0.878 beta, comma beta approximation algorithm for every beta, right? What we proved there is that whatever the best value is, beta, the Goemans Williamson algorithm is guaranteed to get you at least 0.878 times beta. Okay, that like a 0.878 ratio approximation algorithm means this, that you're like 0.878 beta comma beta for every beta. But it can be interesting to look about, you know, guarantees that are not just of this type, like ratio factor times beta comma beta for every beta. Okay. So let me give a couple examples. There's simpler example or algorithms for max cut than Goemans Williamson one. For example, just randomly partitioning the vertices, or just like doing local search in a greedy way, going through vertices one by one and putting them on the better side and then being done. And as we saw before, at least for random partition, these are like a half comma beta approximation algorithms for every beta. I should add here like for all beta, because they're actually guaranteed to cut at least half of the edges no matter what the optimum is. Okay. And here's another like example use of this terminology. There exist 1,1 approximation algorithms for 2SAT. Well, what is a 1,1 approximation algorithm? It's an algorithm that's guaranteed to find you an assignment of value 1, 100%, whenever the optimum is 1. Okay, which means a satisfiability algorithm, or an algorithm that finds satisfying assignments when they exist. Should have mentioned that alpha will always be at most beta. And in fact, it's not often stated this way in like undergraduate classes, but one algorithm that is a polynomial time satisfiability algorithm for 2SAT is to write down a natural LP relaxation and just check whether the optimum value is 1. Turns out that LP opt is 1 if and only if the 2SAT instance is satisfiable. Okay, so that's all I want to say about optimization for now. Any questions? If not, I'll talk about this third task, the certification task, which you might have heard about a little bit less. So here's my definition again. I'll say a certification algorithm for a kind of CSP is any algorithm that, given an instance I, it outputs a correct statement, like a true statement of the form, optimum of I is at most beta star. So it outputs a number, beta star, which it guarantees is an upper bound on the optimum value. And ideally, beta star should be as small as possible. And now we can make a similar definition. We say that a CSP certification algorithm is an alpha beta certification algorithm if the following holds. Whenever the optimum value is less than alpha, the certificate that the algorithm is guaranteed output will be less than beta. Okay, it's always good when the certificate value is smaller. So let me give some algorithms that explain this. And the most canonical example of a certification algorithm, let's forget this alpha beta stuff for a moment. The most canonical example of a certification algorithm is just an algorithm that like takes a CSP, considers it to be an integer linear program, relaxes it to a linear program or semi-definite program, and outputs the like LP optimum value. Right? We're always talking about maximization problems. So the LP optimum value is always an upper bound on the true optimum value, and you can compute it in polynomial time. And so like that's a great notion of a certification algorithm, like just outputting the LP relaxation value. And even better would be, you know, with LPs, they have a dual, and the dual is like sort of a very explicit certificate of a statement like this. It's really just like it's some multipliers for the constraints in the LP, which when you add up the constraints with multipliers, turns into the inequality. Optimum is at most some number. Good. And just to get a little warmed up for this alpha beta notion, let's think about what is a 1,1 certification algorithm. It's nothing more than a satisfiability algorithm. Why? Because what is a 1,1 certification algorithm? It's supposed to be an efficient algorithm that has the following property. Whenever the optimum value is strictly less than 1, so whenever it's unsatisfiable, the algorithm outputs, like beta star, less than 1. So it'll output a number less than 1 together with the guarantee that the optimum is less than 1. So it's an algorithm that whenever the instance is unsatisfiable, like is guaranteed to like say, I certify this instance is unsatisfiable. Okay? And so in that way, it can be used as a satisfiability algorithm. You run the algorithm. If it certifies unsatisfiability, then you're like, great, it's unsatisfiable. And if it fails to, if it outputs like 1 as its number, then you're like, well, it must be satisfiable. Okay, so now in the remainder of the lecture, I want to talk about this kind of confusing point. Like, what is the difference or what's the deal with approximation versus certification? Because it turns out they're both very important problems in the study of CSPs and algorithms, and they're different problems, but like the difference is kind of subtle. So let's talk about this now. An alpha beta approximation algorithm searches for an assignment. It's like a search problem for an assignment. Okay, and just to remind you, the guarantee is that when the instance happens to have value, optimum value at least beta, the algorithm will give you back a solution of value at least alpha. An alpha beta certification algorithm also kind of searches for things, but it searches for like a tight upper bound on opt. Okay, so again, it has a property that when the optimum is strictly less than alpha, it certifies the statement like optimum is less than beta. Okay, and now let me try to really clarify the difference here. For the max cut problem, the Goemans Williamson algorithm of first solve the SDP, get the vectors, then do this random hyperplane rounding to convert them to like an actual cut and output that cut. That's an approximation algorithm, right? It finds a good solution. And in particular, like whenever the optimum cut is beta, it guarantees to find a solution that's at least 0.878 times beta. On the other hand, there's like a lesser thing you could do. You could just solve the SDP. Maybe you didn't even figure out this random hyperplane thing. You just figured out, oh, I can write down this SDP, which is a relaxation, and therefore the SDP optimum value is an upper bound on the true optimum. Just solving the SDP and outputting the SDP op number is, I claim, a certification algorithm. Actually, that's clear that it's a certification algorithm. It's just because the SDP opt is always at most, or yeah, it's like an upper bound on the true opt. I also claim, though, that it's a certification algorithm that's like 0.878 beta comma beta. And let's really understand why this is the case. So let me dive into this question. I claim that outputting the SDP value is a 0.878 beta comma beta certification algorithm for every value of beta. So why is this true? Well, fix some number beta. Fix a number beta. And suppose you have a graph G whose maximum cut is strictly less than 0.878 beta. Could it be that when you write down the SDP for this graph and compute its optimum, the optimum is at least beta? I claim no. And if my claim is true, then I have shown that this outputting the SDP opt is a 0.878 beta comma beta certification algorithm, because I've shown that like whenever the opt is less than 0.878 beta, the SDP opt will be less than beta. And therefore the certified amount that you'll output will be less than beta. So why is it true that if the true opt is less than 0.878 beta, the SDP opt will also be less, that it could not be at least beta? The reason is we happen to know the Goemans Williamson algorithm, hyperplane rounding algorithm exists. And we know that the hyperplane rounding algorithm has the property that if the SDP opt is at least beta, it would find a cut achieving value at least 0.878 beta. But that's impossible because we're assuming the graph's max cut is less than 0.878 beta. Okay, so therefore, the existence of this hyperplane rounding and its guarantees tell you that when the opt is less than 0.878 beta, the SDP opt will be at most beta. So just outputting the SDP opt is at most is a 0.878 beta comma beta certification algorithm. So probably like you wouldn't know this fact about the algorithm that just outputs the SDP value unless you figured out this hyperplane rounding stuff. But nevertheless, this is the case. And in general, this same phenomenon always holds, and you can check for yourself that this is true in general. Whenever you have an alpha beta approximation algorithm, it's also an alpha comma beta certification algorithm. Good. So the one thing I'm trying to conclude here is that the approximation task is strictly, well, it's at least as hard as the certification task. I got a question here which said, do we have to talk about the de-randomized version of the hyperplane rounding instead of just the randomized rounding? Good question. I've kind of been brushing the difference under the rug. Actually, for making this deduction, we don't, because actually, even if you just know that the hyperplane rounding has the property that when the SDP opt is beta, the expected value of the cut is 0.87, at least 0.878 beta, then you can say, oh, by the probabilistic method, if the expectation is at least 0.878 beta, there must exist a cut, yeah, whose value is at least 0.878 beta, which contradicts opt less than 0.878 beta. So yeah, so you don't need it to make this deduction. And one reason I'm glossing over it is like basically, whenever you have a randomized approximation algorithm like this for a CSP, you can convert it to like a de-randomized deterministic one very easily. In particular, like you can run it like n times and pick the best solution that you get. And then a simple Markov argument that I'll let you think about shows that with high probability, you'll find a solution whose value is at least the expected value minus 1 over n. So that's why I'm always glossing over, like I don't mind if the algorithms are randomized and we only care about the expectation. Okay, so let me conclude with one long slide. It's a tale of the Goemans Williamson algorithm on 2 graphs. Actually, I should mention that I only have like 2 minutes left. So I'll give this slide, and then I have a little bit more content, like 1 or 2 more slides that I'll add to this video at the end, in which I tell you what is the PCP theorem and what is the unique Goemans conjecture, among other things. But let me end just this portion by talking about the Goemans Williamson algorithm on 2 graphs, because I think it'll illustrate this difference between certification and, well, it'll illustrate like another confusing point, potentially confusing point. So the first graph I want to talk about is, looks kind of like this. The vertices are the corners of a cube centered at the origin, but I don't put in the normal edges. Think of this cube as sitting in, high dimensional space. I connect 2 vertices by edges if like the origin is here, and I consider connecting 2 vertices if the angle between the vectors going to those corners is at least 3/4 pi, or 135 degrees. Okay, so this vertex, it's connected to like the vertices that are kind of like sufficiently far away from it. So the dotted things are not the edges, the yellow things are the edges, and you have the same picture for every vertex. So I'm just going to tell you some facts that are not necessarily easy to prove, but they're true. So the first question is like, what is the maximum cut in this graph? the maximum cut in this graph, you might guess it. If you actually take any axis parallel hyperplane, it turns out you can prove that this is the maximum cut. And once you know that, it's not hard to show that the actual optimum value, fraction of edges cut, is basically this quantity, half minus a half cos 135 degrees, also known as half plus 1 over 2 root 2, which is about 0.85. So in this graph, the best, at least in high dimensions, the best cuts about 85% of the edges. Now, what about the SDP algorithm? Well, remember, in the SDP algorithm, you're trying to assign a unit vector to each vertex. And our graph is already kind of geometrical. And in fact, it turns out that the optimal SDP assignment of vectors to vertices is like the identity mapping that just assigns each vertex to like where it really is in space. And you can show that the SDP opt value is equal to the true opt. The SDP opt is 85%. So here, like, the SDP has done a perfect job of certifying the solution. It says it's at most 85%, and indeed the opt is 85%. But if you do the Goemans Williamson random hyperplane rounding, it'll not produce an axis parallel hyperplane. It'll produce some, like, random one. And you can show that it, in expectation, will give a cut that only cuts on 3/4 of the edges. This is the same 3/4. So it only cut 0.75 of the edges. And by the way, this 0.75 over 0.85 is really close to this 0.88 value, 0.878 value. So this is a case where the optimum SDP opt value gives a perfect certification, but the algorithm only gets a 0.878 factor as like a search optimization problem. On the other hand, there's the opposite occurrence for a different graph. It's interesting. So you can take another kind of geometric graph where you take a sphere in high dimensions, a unit sphere, and you set the vertices to be quote unquote all points on the surface of the sphere. Okay, you have to, like, to make it a finite graph, you have to discretize this instance, but just imagine like you put in all points. And you use the exact same edges. For every 2 points in the sphere, you connect them if their angle is at least 135 degrees. So each point is connected to like a bunch of points that are like quite far away. For this graph, some other interesting things happen. It's perfectly rotationally symmetric. So the best cut in this graph, this is hard to prove, but it's true. The best cut in this graph is any hyperplane through the origin cuts. And any hyperplane through the origin cut, you can show cuts about 3/4 of the edges. So opt is like 3/4. If you give this to SDP, it turns out again that the best SDP solution for associating a unit vector to each vertex is like the identity mapping. You just let the vertices be themselves. And then you can show the SDP value is bigger. It's this 85% number. So this is a funny case where the SDP is like a relaxation. It's like as far away from the optimum. It's like 0.878 away from the optimum. It's bigger than this 0.75. But ironically, if you do random hyperplane rounding on the vectors you get back, you get a hyperplane through the origin, and those are optimal. So this is a case where the random rounding algorithm actually will find you an essentially optimal cut, a value 3/4, even though the SDP opt value is off. Okay, so this situation is a good pair of situations to keep in mind when you're trying to understand the difference between sort of certification algorithms and approximation algorithms. Okay, so let me end the lecture there. As I mentioned, I'll add like 5 minutes onto this lecture later. I'm going to stop the recording now, but you can feel free to stick around and ask me any questions you have.